Taylor series error. Okay, so the first thing you want to keep in mind is the Taylor polynomial versus the Taylor series. Okay. So if I were to have a function like sine x, right? You can write the Taylor polynomial approximation to whatever degree, right? So what is the approximation for sine x? Nobody's memorized it yet?
Right here.
It's the Taylor polynomial.
-1 to the power of n minus 1, right? And then times n minus 1 to the power of n over n factorial.
So it's 0?
Huh?
It's not x, n minus 1, it's x minus n to the n.
Right.
Right? So this would be degree 5 Taylor polynomial. Centered at zero. So we can make that into a Taylor series by making it infinite and writing it as a sum. Okay. Shame on me for not having these memorized, I guess. Huh?
So what's the real life applications for Taylor series and polynomials?
I'd have to think that through, to be honest with you.
Is this one of those math things?
Well, okay, the biggest thing we had them for was to approximate values of functions without a calculator. So, thank you for leading us right into my next point. Let's see, the Taylor polynomial degree 5, right, versus the Taylor series. This series, if we wrote this, like if I put a 5 here instead of infinity, that would generate the same equation. Okay. So again, one of the points of this in the past, so we don't really have an issue with this anymore, is to approximate values of functions. So let's say you want to approximate or find the value of sine at 1. Not unit circle friendly, right? Is 1 close to any unit circle value you can think of?
Pi.
Pi over 2 is 1.57. What's pi over 4? Yeah, it's somewhere in point range. So that's pretty close, right? So we can say those are pretty close, right? Right. But is there some error here? Yeah, there is. We can use Taylor polynomials to reduce that amount of error. Okay. So I can use this here to calculate the value of sine at 1 to a certain degree of accuracy. Just plug in. So f of 1 is approximately, it's still an approximation. 1 minus 1/6 plus 1 1/20. Is that right?
So what is factorial?
5 times 4 times 3 times 2.
Oh, okay, so
Just
just
5 factorial. You just multiply everything every.
Which one's really close?
So if we really want to get a nice pretty number, we can do common denominators because we're not calculator based here, right? 6 times 20, right? It's 100 plus 1, so 101 over 120. If you want to do long division, you can get a decimal. We can get ridiculous, right? Okay, now wait. So, but is that perfect?
No.
no.
Okay, so question is, how close to perfect is it? Okay, how close is this? To sin at 1. And that is exactly what error bounding is all about. How close is your answer to the actual answer? Okay. It's what?
2000s?
It's within 2000s.
No, 210,000.
So 0.0002. Cool. Okay, so you can see that even just the 3-term Taylor polynomial gets really, really close. Close enough in the old days for them to operate just fine, right?
Yeah. but
Nowadays, our tolerances in manufacturing stuff are so tight, that's probably not enough.
Seriously?
Okay. 2 10,000s? Like if you look at car engines, for example, over the last 40 years, you take a truck like my 79 Ford, it's 40 years old. It's got a 351 in it. We use 10W40 motor oil. Okay, you take a truck now with a 5-liter engine, which is pretty darn close to 351. They're now using 5W20 motor oil. So it's thinner. Why is it thinner? Because everything in that engine is tighter. Like the manufacturing is so much more precise. The bearings fit tighter, the rods fit tighter, everything fits tighter, so you have to use a thinner oil, right? So maybe not close enough. Okay. Fortunately, computers make things really easy to get pretty darn accurate. Okay, so here's what's nice about this is an alternating series. Right? Okay, because we have alternating signs. Remember I told you how to recognize alternating series. That right there. Correct? If you have an alternating series, the error is bounded by the value, by the absolute value of the next term.
So,
Okay.
1/7 factorial is 2 10,000?
That's the next term, correct?
Right.
So this approximation for sin at 1 is within that amount of the actual value of sin at 1. Okay.
So the higher, okay, so the farther.
So our max error, so 1/101 over 1/20 is within 1/7 over 7 factorial, whatever that is.
Oh, that's wow.
of sine at 1. Because the absolute value of that, right? Okay, so what's 1 over 7 factorial? Or
19 10,000ths. So 1 over 5,040.
with that number?
Yeah.
What, 0002?
That's insane. So is that like a fun fact or is that something?
No, this is something you can calculate.
Well, do you actually like need to know that? Like, you know?
It's an AP exam question every couple of years. There's always a serious question on the AP exam. They will ask you to write these out, Taylor polynomials. They'll ask you to approximate values. They'll ask you to find the error bound.
Like a short answer?
No, it's number 6. For response number 6 is always a serious question. Okay?
So if it was, the error was that.
So it just says that the error is less than or equal to this.
Okay, it's not exactly
No.
that. Because if it was exactly that, all you have to do is
That's
add
the key
that.
there,
Okay.
within. Okay, so we know that we can say in manufacturing, we can say we want to be within 1/1000th accuracy. And you can figure out how many terms you need to calculate. Okay, so, but this would be figuring out how accurate you're already being, right? Versus the other way to do it is to make sure that I'm going to write this correctly. I don't want to mess it up. Oh, I know it's not. I had to go to chapter 10 to get a good example here. Okay. So, let's say we have this series. Right, so the first thing you can be asked is show, and this is a notation thing. Okay, that right there. Okay, this is like code for show that the sum of the first 6 terms has an error less than 1/7. That's what that's saying. It's just the mathematical way to write it. It's the same thing we just did. So, this is alternating, correct?
Yeah.
We have the sum of the first 6 terms. So what term do we use for error? The 7th term. Okay, so.
So then can we just jump to the 7th term?
Put that into the equation. No, because you have to find.
Okay, so we use the 7th term
Well, I mean, if you know the
as the
equation.
bound.
You need a certain answer.
What is the 7th term? Absolute value. So absolute value. So we don't even worry about the alternating part anymore.
Right.
That's the all.
So then it's 7 over 7. Or it's 1/7.
It's negative 1/7, absolutely.
No. Yeah, so.
7 minus 1 is 6. Negative 1 to 6 is 1 over 7 because n is 7.
Yeah.
1/7. You're done.
Oh, that's it? What the? Sweet.
Yeah, that's it. It's an alternating series. That's what makes this nice about alternating series. We'll talk about series that do not alternate tomorrow
Different equation.
and the next day. Okay, but alternating series, next term, error bound. Okay? Good with that?
You can't do airbound with
Oh, wait.
alternating
You
series?
can, but it's more complicated.
Why?
What,
So we're wrong?
Because an alternating series, what it does is it adds positives and negatives,
Yeah.
right? So the next term is the top ceiling for how far away from the x-axis that would be.
But equals 1/7 is not included.
But as opposed to a non-alternating series, which is gonna add like this, it's still increasing, but.
Yeah.
Okay,
Mr.
Mr.
Arthur. Backwards? It gets smaller as it goes up?
Yeah, alternating series,
No. For non-alternating, the values get smaller as you go on. Even though they're positive, they get closer to zero.
the value of each term gets smaller,
Yeah.
but the sum's still growing,
Oh, yeah.
Mr. Arthur.
so. Okay, we'll get into that in chapter 10. Okay, so, alternating series.
Would that be less than 1/7 then?
Yeah, it would be.
Okay.
So the
You're
error,
just proving it.
so S minus S6
So you're proving it.
less than 1/7. You could make that statement.
Okay.
Okay, the other thing you need to do is,
Proving it. You don't need to state that.
find an n such that
See, you can do the service monitoring.
S of n has an error less than 10 to the negative third.
There was anger.
So 1/10,000?
1/1,000.
1,000.
10 times 10 times 10. Okay, so again, alternating series, what term do we use for error?
The one after?
Yeah, so if we have a series that has n terms,
N plus 1.
or, right? So we have the n plus 1th term of this series, right? The next term is n plus 1. Now you just do some algebra.
Solve for N, is that it?
Yeah.
What the heck?
So you just solve for n?
Yeah, solve for it, so.
I think you can just get rid of the memory. Save like cost multiplier, that's it.
Because you multiply by inverse one.
Because you got 1/1 top, 1,000 over 1,000. So negative 999 over 1,000.
Just kidding, I was right.
Wait, but I feel like you're murdering puppies right there.
No?
Does it?
Because that was just an x and you can multiply by x on one side, so that means the x.
Oh, hold on.
I thought the sign
Yeah, wait.
This the term has to be bigger. So any term, any number of terms past 999 will get you an accuracy less than or equal to 1,000.
Oh.
Alright, I have an algebra question. How
Okay.
come you're just able to like get rid of the numerators? Don't you have to like multiply across?
Well, you cross multiply.
Then wouldn't the
Yeah, it doesn't
sign
say-
changes?
Oh,
Yeah.
I was correct.
What?
I was right when I had that there, right? That was correct, now it's right. Because if you have n plus 1 is greater than or equal to 1,000. Sorry, the error, the next term has to be less than this error bounding, right?
Oh,
So when you do
okay.
the algebra,
So well, n is great, okay.
this works out. Yeah, so if you have 999 terms or more in your series, you have an accuracy of less than 1,000. And you'll set that next term less than or equal to your error bound. Okay? Questions? It's really the two ways you can tackle alternating series. 6 problems.
Only 6?
Handout.
Ooh, a handout.
Ooh, handout,
Yeah.
yes.
This is a new day this year that I actually threw in.
Wait, you didn't do this before?
No.
Chapter 12 worksheet.
Okay, so
No.
And do it, do your
Oh,
workout.
yeah, and
Is
there's-
Danny
So, one more thing that I did not mention here.
I'll be the genius.
So if this
that?
is our approximation, right? And this is our error bound. We know that this is, the maximum would be to add this,
Still another direct.
correct? And the minimum possible value would be to subtract. That's part C of the first question, right? This is an interval at which this has to be in between, right? Yep, there you go. Bring questions tomorrow.